Now, in this chapter, I would like to introduce the first and oldest protection principles, which is overcurrent protection. Now, overcurrent means any current higher than normal or full load currents. We call it overcurrent protections. But any current that we have a threshold, a setting, and anything higher than threshold, we call it an overcurrent protections. Based on this, like a fuse an overcurrent protective device. Okay, a fuse in our the plugs are 13 ampere type. So if the current exceeds 13 ampere, I'm expecting fuse will blow, okay, within a certain time. Okay, so this fuse is an example of an overcurrent protective device. Now, how do you implement the overcurrent protection in a relays? So what I would like to cover in this course, what is an overcurrent? How do you connect the relays and to detect some overcurrent conditions, type of overcurrent relays, coordination of overcurrent relays, how do we discriminate between the relays, so that you want to detect the location of faults based on based on current magnitudes or based on timing. There are also procedure you need to follow to set overcurrent relays, okay, and also I will give you design example. So overcurrent relay are majority of feeders and distribution systems are protected primarily by overcurrent protections. So this is considered as the primary protection in distribution system. However, in transmission system, overcurrent protection is, let's say, a backup protections. You can have phase overcurrent protection and ground overcurrent protection relays. For criteria, say normally any current higher, normally short circuit is much higher than full load current. So any current higher than full load, this is the presence of a short circuit or an overload conditions. So how do you connect a relay and overcurrent? So suppose you have 3 wired systems. This is 3-phase systems. I'll put a CT in each phase, and CT secondary of each phase connected to one phase overcurrent relay. This is an electromechanical relay, for example. In numerical relay, all of this is inside as one relay, okay, or functions in a relay. So an electromechanical relay, this will be for phase A, phase B, and the text relay 3 is phase C, and the star connection of these 3 are connected to a 4th relay called air fault overcurrent relay. Okay, so this is the air fault relay. And at that time, in electromechanical relay, to save money, they could eliminate one of these overcurrent relay. And by these relays, we can also detect faults in the 3 phases. So if we have, for example, one phase to ground, let's say, suppose I have phase to ground faults. Okay, now in this phase I have fault, but this is no faults here. So I will have a current, very large currents here flowing, but normal currents here. So this relay will detect it as high current passing and will trip the circuit breakers. Okay, but this current also flow here because this current I ground or I neutral, okay, IG for the ground fault relay is the summation of the 3. Okay, and the summation of 3 is 0 during normal operating condition. When these currents are summed 0, means also these currents are also summed 0 during normal operating conditions for a balanced operating conditions. But during false line to ground, I have a current. If you sum these 3, suppose this is if you sum these 3, will not be 0, so it will be a current flow on the air fault, and this also will detect that there is a fault in the ground and will operate. So these two will operate during airfall predictions. However, this is much sensitive than this to detect ground fault. I will show you later why. Okay. Now, if we have face-to-face faults, suppose I have faults between these two phases, then current IA in this direction, current return in this direction IB. In the here also will have current IA. Okay, suppose dot marking is this current leaving here, this corresponds current entering here, this is IA. Okay, in the secondary side, and for this phase, because the direction in this direction, so current entering dot correspond current leaving a dot, so this IB. So the current IB in this direction and current IA in this direction. Okay, so the current will flow something like this. And as a result, if this current in the secondary side higher than these two pickup setting, this relay and this relay will operate, indicating a force between B and C because both these two has operated. However, the current IG, when you sum the three, right, this current, because it is equal and opposite this current, the summation of these two becomes 0. Okay, so there will be no current flow here, right? And this will not operate in this case. And similarly, if we have three-phase fault, there will be three currents here, but they are equal magnitude and displaced by 120 degree. So all the three will operate. Okay, however, there will be no currents here, so I can know from the operation of the three that this is a three-phase fault. Okay, we can also connect the relays in case we have three-wire system like line 1, line 2, line 3, and ground and neutral. Okay, and in this case, I have to make sure that this ground fault is the pickup setting not less than the normal neutral current. Okay, so in order to reduce the sensitivity of this, I have to put another CT in the neutral so that the current, neutral current that comes from the summation of 3 will be eliminated with this. Okay, so that here will be the net I lines, the three currents minus the I neutral, give you the ground current. Okay, if there is any ground current. So suppose I have a load now connected between these two, between C and neutral. So in normal operating, I have a current passing here, right? So if I have this one, so there will be a current also following here, because if I have this marking here, current leaving here, this correspond current entering. So I have a current here flows, and the neutral of this is the dot marking. The current entering the dot correspond current leaving a dot. Okay, so the current in the neutral in this direction. Okay, and the current in the phase C in this direction, and because this is equal to this, okay, suppose I have no load connected here, so this will be 0, 0 here, so the summation of here will be 0, right? So this will be I ground becomes 0. There will be no current because this current is equal to this KC at this point becomes 0. Okay. However, if this is not done here, if I didn't do 3CT to eliminate this, then if I put a load here, and so that current will correspond to a neutral current, so that's in this direction. And I suppose there's no load here, so that current will be same as IG. So I have to make sure that the setting of this higher than normal maximum neutral current. While in this case, I don't have to do this. I can even go below than normal, much below than normal. So this is more sensitivity. Sensitivity of this is much better than this. But I have to use a fourth CT on the neutral. For the ground to detect this, to set this one, the settings of these are to set these, or the phase over current relay are set. Setting here has to be greater than I full load. Okay, while this ground relay, settings of the ground relay has to be greater than a normal ground imbalance current that will flow in the ground. Okay, so that will not, it's not full load, it's much less full load. So we said it's be greater than 0.2 to 20%, okay, of I full load, or sometimes to 30% is enough. So why 20% higher? But just to make sure that it is during normal operating normal imbalance system, I have a current here which represent not a fault conditions, but this is a normal current that will flow due to a normal imbalance in the system, allowable imbalance in this degree of imbalance in the system. So the settings of the ground relay. So how do I set this one, the ground over current? Just you to take 20 to 30%, 20 to 30% of your full load. Okay. So I don't have to know. Okay. Now, how numerical relays are connected? These in numerical relays. Now, this is like I have a machine or a transformer star winding, right? So on the star, I have a neutral conductor. In the neutral, we connect a CT, and the CT is connected to array. So this is one way to detect the fault to ground by monitoring the ground wire current. Okay. So if there is any normal operating, there should be no current here. It's only during fault you will have a current flow here with tally, and this because this it can detect the flow abnormal, this abnormal conditions. I can instead of this, I can also put a CT, a summation CT, where I sum the currents here, and then I connect it to a relay. This is another way to detect also the ground. Okay, so I have no CT in each. I have just one CT through which all the conductor passes. Okay, and this is also air fault relay. Air fault relay. Okay, by using summation CT. This is called summation CT. And however, summation CT is this. Now this is summation CT. Okay, and this is the 3 CTs for each current. So with this relay, I have to have a channel for phase A, channel phase B, channel for phase C current, and a channel for we call this zero sequence current or summation CT current. Now, how do you, this is the numerical relay, okay, microservice relay. It has, now I connect phase A, CT, the output of phase A to first channel. And this is like auxiliary transformer and so on. And this manufacturer, they give me, I can connect each channel either to 1 ampere or 5 ampere. It depends on these CTs, the standard output of 5 or 1. Now for IEC standard, say the standard output secondary current, rated secondary current is 1 ampere, so I'll connect it to the 1 ampere channels. I'll connect it this here. Okay, the second channel will go to the next one. Okay, so the second channel goes to the second one, and the third channel goes to the third one. Okay, the third channel goes to the third one, and then the remaining, the output of the 3 channels, so they go out from this one, joint with the second one, okay, joint with the third one, okay, and this is now, it returns back to the star point of the 3CT. Okay. So this is equivalent to this, the 3 units of this. Now, how do I connect this one? Now, if I have a ground element, so before I return it, if I have this unit, so instead of doing this, okay, I would, if I want to connect something, if I have another channel, I can estimate this by adding these 3 inside the relay, or can also make a summation of this and enters to a fourth channel. So the channel 1, 2, 3, this is the fourth channel, input channel. So how do we do that? So instead of this, I would do the following. So I will, instead of returning this to the CT, I will connect in this way. I will go take the star point, goes to the fourth channel. So fourth channel, this monitoring the ground current, so which is I not zero sequence current. So this corresponds to IG, because summation of the 3, IA plus IB plus IC give me, this is IG, ground current, or I naught. Okay, the output of this channel returns back to then the star point, which is this one. And this is Argand. Okay, so this is how I connect a microprocessor relays, okay, whether to the 1 ampere or to the 5 ampere 3 channels. So this manufacturer gives us 6 channels for the current, so that I can, this is 4 for 1 ampere and 4 for, so I have 8 channels here to implement overcurrent relay. And plus, so instead of doing this, if I have a summation CT, then if I have a summation CT, if I have summation CT, then I can connect this to, I can do this also, but I can use this directly. I'll show you. Suppose I have one channel. Oops. So in this case, I'll take this to the ground. I'll take this to the ground here. Okay, then I will not connect this anymore. And the third channel connected to the fourth channel. This I'll put it on purple. So this one I'll take it from here to this one and returns back to the summation CT. So this is now I'm detecting I connected something like this, the fourth channel. Okay. So depends now availability of the summation CT. Summation CT much sensitive than you sum the 3 currents and you take it to the other one. So this is 2 alternative I can make. Okay. And this is the output of the trip outputs. I can detect if there is any pickup of fault. I can take the output here, or from this you can program from any of these channels. And you have also input, digital input channels. We have 2 input digital channels. And we have also a power supply, or this is for communication ports, RS485. And we normally have a power supply, DC power supply, whatever. So this is an example of an overcurrent relay, okay, a commercially overcurrent. This is from MyCom P120 or P122, an overcurrent relay. What types of overcurrent relays, types of overcurrent characteristics? Time current. So this is the time versus current characteristics. We have something called an instantaneous overcurrent, and this code, numerical code according to IEEE is 50. So this characteristics of any current that the relay sees higher than a threshold I setting, okay, any current that passes in a relay higher than this, the operating time is instantaneous. This is almost less than 0.1 seconds, instantaneous. This is less than 0.1 second, very fast. Okay, could be sometimes 40 milliseconds. So 40 milliseconds too. Okay, instantaneous. There is no time delay. But if the current's lower than this, the relay will take infinity time. So it means will not operate. Here operate instantaneously and operate during this range of current. Here restrain will not operate. Okay, we have another types of, this is called instantaneous. There is no time delay settings. Only what you need a set is a current setting. We have something called also time definite over current relay, where I have a time settings and a current setting, but in this time setting I can adjust this time. Like now I have a current. If the current exceed I setting, like a current somewhere here, instead of instantaneously trips, I want to delay with this time. Okay. And this is not changing. Whether the current this value or this value or that value or this value, any current higher than this, I want to delay the trip by a time t from the occurrence of current higher than I setting. So it is called definite time because time is fixed. But yeah, adjustable, but once you adjust to a value, it will be fixed operating time. And this is no operation region, okay? No trip, no operation, no operation region, and their trip region. But after this time. And we have also time. This is time also, time over current relay. This is also 51, is regarded as 51, but it is anything instantaneous 50, anything with time delay is 51. This is also considered as 51, but definite time. The 51, we can also make it inverse characteristics. So this is time versus current, or versus plug setting multiplier. I mentioned about this before. Plug setting multiplier is the current multiple of the pickup setting. So I1 means the current is equal to the pickup setting, 2 twice the pickup setting, and so forth. So when the current passing in the relay equal to the plug setting, you want the relay to operate. It will take infinity time. Okay. And but when the current's twice the pickup setting, it will take, let's say, this operating time. When it takes, let's say, 4 times, it'll take this operating time. So it's inversely proportional. That's why this character is called inverse definite minimum time. And why this definite? Because at the end, if the current is extremely large, the current will be almost definite. Okay, it won't change lower than this. And now to change the time, suppose I want at this kind, this is the operating time, but I don't want the operating time this. I want to be at larger than this time. So then you adjust the time dial setting, or TMS setting, time multiplier setting, which is the dial on the top of the relay, an electromechanical relay. So I can choose time dial setting higher than time dial setting here. Okay, so that time dial 1, time dial 2. So I can adjust the time at that particular time. Now to coordinate between different relays, So in radial systems, like you have and these are three buses or three lines, radial feeders. I have loads. Suppose I have load at each feeder. Okay, so these are loads, and I want to coordinate. I have protection relay, overcurrent protection relay here at the beginning of each feeder. And as I mentioned, in radial system, I don't have to have another relay at the remote end of the line of the feeders. Okay, because current will not reverse. I have no source at this time, so it's sufficient to have an overcurrent protection and a breaker isolation at the sending end of the feeder. Now suppose I have a fault here. You want this to operate, right, first, because this is their primary now concept protection for this. Now if this fails, you want this to operate as a backup, as a remote backup. So how this knows that this did not operate? I can this can know this if did not operate or not based on time delay. I will delay this more than the operating time of this. So if that time elapsed, finished or completed, and this didn't operate, then this would act then. And similarly, this will delay more than this. So if this fails, this also acts as a backup to this. However, if the fault's here, this will not see the fault because the fault behind it. So there is no current flowing here, especially if this is three-phase fault, solid fault. All the current will go here, and no current flows to the relay tube. So in this case, this will see the fault, but how? Because of time delay, this would wait for this one. Okay, but if this time elapsed, then this will take action to clear this fault, and this work as a backup to this. Now, how do we set the sequence that 2 waits for 1 to operate first and 3 waits for 2 to operate first? This is called the coordination, and 4 waits for 3 to act first. If we do the sequence of operation, we call these relays are coordinated, and once they are coordinated, I achieve selectivity, that only faulty elements is cleared. Okay. Now we have 3 ways to achieve selectivity between to identify fault location. Okay. One by time grading, second by current grading, third by time and current. When I use time grading, okay, all what I want to do, I want to set this at the lowest time, let's say 0.1 seconds. This is at higher time, let's say 0.5 second. This is more time, let's say 0.9 second. And this is at larger time, let's say 1.3 seconds. I added 0.4 seconds time difference between them, okay, so that this will always, the backup always wait for the primary to act first. This is called time coordination. Okay. So for the faults here, if this sees a fault, then it will take 0.1 seconds to operate. Now, if 0.1 second has finished and this still current passing, fault current passing, this will, after 0.5 seconds, this will act. Now, if this still passing and this didn't act, this will, after 0.9 second, will act, and so forth. So this is called coordination by time. Okay. With this, I can use definite time settings. Any current higher than settings, you detect a fault, then you just wait. I'll set one of them at 0.1 second, another at 0.2 second, 0.5 seconds, the third at 0.9, and fourth at, okay. So I will use here the 51 or definite time over current protection relay or function for time grading. When do you use time grading? You use time grading when the Z source is very large compared to Z line. And so in this situation where the fault current at the remote end and the fault current at the local are very close to each other. Okay, and this happens when the Z source impedance, Z source, very large compared to Z line. Okay, I'll show you later. So in this case, you cannot identify faults from here. This current may be 1001 kilo ampere. This may be 1.1 kilo ampere, very close to each other. You don't have margin. So in this situation, you cannot identify fault location based on current magnitude. And then we go to grading by time, okay? In the second type, grading by current. Grading by current is used when the source impedance very, very small compared to line impedance, or in situation where the fault current at the remote end and local end has a large difference. So suppose here 1 kilo ampere fault current, this is, let's say, 10 kilo ampere, okay, or 5 kilo ampere. There's a large difference between them. And based on this large difference, I can identify a fault based on current only. I don't have to have time settings, okay? So, so suppose now, in the same situation, this 1 kilo ampere here, and here the current is 5 kilo ampere, and current here, fault current here is 10 kilo ampere, and here let's say 20 kilo ampere. How can I? Now there is a big difference between a local fault at bus this, and fault here. So why do you have to wait for 0.1 seconds here? You can instantaneously trips. If this relay sees more than 1 kilo ampere, it means a fault somewhere here, closer. The closer the fault to the source, the larger the current. So this relay, okay, can decide or can guarantee the fault in this line if the fault exceed 1 kilo ampere, okay, by, let's say, 25 margin, 25%. So if I fault, let's say if I fault greater than this relay at 1, greater than 1.25, for example, of I fault at remote bus, then a fault in this line, and you can act. We don't have to wait. And similarly, if this is a fault larger than 5K, then a fault is not here, right? It's a fault somewhere here. For a fault greater than 5K, by a degree, let's say I'll take 1.25 times I fault remote, which is 5K, then I don't have to wait. This can act immediately, okay, to clear the first faults. So with implementing this, I can use this functions, which is the instantaneous. This is grading by current only. It's not grading by time. So all of these relays acts instantaneously. Okay. The third coordination that you can make is grading by current, time and current, where I'll use both current, grading by time current, still is used when Z source much smaller than Z line. You have a margin between, a large margin between fault local and remote. But here you use both time and current for grading, okay? like you use time inverse current rate. So like this is for relay number 1, characteristic, relay number 2, relay 3, relay 4. I use just different time dial settings for them. And now suppose the fault is here. So, and that fault corresponds to this value, okay? So at that fault, the relay 1 will take this time to act. So it will operate first. Now, if this did not operate, then relay 2 will take this time to operate. Now, once this operates and this is cleared, open, then there will be no current flow, so 2 will reset because it will take this time. So this will operate before the second one operates. Once the current reduced to 0 after the operation of 1, 2 will reset. So it will not reach this time, okay? So as a result, 2 will not operate once 1 operates. However, only to operate if 1 failed to operate, then like the current still flowing, and this time passed, this time has passed, and we reach that time, then 2 operate. Similarly, if 2 failed and the fault is here, then 3 will operate after this time. So what is the time difference that we should keep between the relays? We call it the coordination time interval. This time called the coordination time interval, or we call it sometimes grading time. Grading time. Now, how do you decide this grading time? Should I leave 0.1 second enough or 0.4 second enough? It depends on the technology used. Are these electromechanical relays? Are you coordinate a relay with a fuse? Are these circuit breaker, low voltage circuit breaker with a low voltage circuit breaker? Are these two numerical relays? So this time depends on the type of circuit breaker that have used and the type of relay that are using, relay technology. So this is just a comparison between comparison. If you add the two characteristics, if you add definite time, use inverse time characteristics plus definite time. If I use definite time, then the last one, the faults here, it will take this time to operate. This is the characteristic for the last one, okay? And this characteristic for the second one. So if the faults here, okay, somewhere here, it will take instead this time to operate. If the faults here, it will take breaker 2 will take this time to operate. Okay, so if the faults here, this will not operate because it will take this time. This will trip before this. And similarly, if the faults here, this relay characteristic, something like this, will take this time to operate. So this is grading by time. Now, if I add grading by inverse time characteristic, the characteristic looks like this. I'm just plotting distance versus this versus fault location. Right? Instead of this is distance rather than current. Okay. Now, if you plot here current, if you plot this character against distance, the larger distance of the fault from the source, the larger the source impedance or the fault impedance, then the smaller the current, because current is equal to the voltage of the source divided by fault impedance from the source till fault point. So the larger this farther the fault from the source, the larger Z fault and the smaller I fault. Okay, so at smaller faults, you mean you take longer time. So I can plot this against, I can plot the same curve with distance. It will be like this. As distance goes farther away, impedance increases, current reduces, and because current reduces, time will be higher. So so can say distance with time. So the characters will look like this. So this is at minimum distance, this is at longest distance. So the characters can be plotted like this. For relay 1, this is for relay 2, this is relay 3. You combine these two, as you can see, if I compare the instant time definite characteristic with inverse currents characteristic will give us better, faster operating time, because like for a faults here, if I use a definite time, it will give me this time. But at that fault time, the inverse current characteristic will give me this operating time faster than this. So for faults very close here, it will give me this time smaller than this. So that has better characteristics as compared to the. If you combine now instantaneous with inverse time, I will close in 1 minute with this. If you add these two, like I added an instantaneous characteristic, which is like this, okay, with inverse current characteristics. So like this is the inverse time characteristic, IDMT characteristic, and this is the instantaneous characteristic, right? If you combine these together, you will get, so this plus this, you will get a characteristic something like this. Okay, so this is current versus operating time. All right, so this is like the characteristic instantaneous. This is the time inverse current characteristic. So you combine them, you get this characteristic. But if you plot this against distance, the character is something like this. Opposite to that. Okay. So for faults here, this will operate. Okay, so what I did, this is the 51. This is the characteristic of 50. So if you combine them, you get this characteristics. Now fault somewhere here, then the 51 will operate after this time, but the instantaneous will not operate. If the fault is very close to breaker 1, the current is high somewhere here, so this characteristic, the inverse current characteristic will not, the instantaneous relay will operate before the overcurrent, the time overcurrent characteristics. And similarly for relay blue 1, this is the characteristic. For the relay 3, the relay 3 is this. So if the fault somewhere here, okay, 2 will operate directly within this time, instantaneously. Okay, we'll close here. Inshallah, I will cover this in the following lecture, right? To give you an examples and the procedure you should follow to set these timing and set how do you choose the current pickup settings, the time difference, and so forth. Any questions?
No, thank you, Doctor.
Okay. Now, before you leave, I'll stop the recording.